Swayam Prabha. Digital India. Educated India.
The matrix decomposition. So, earlier we studied the fundamental of the ideas. Now we have to go to the matrix decomposition. So, if we start with matrix decompositions, first of all we have to know what is the meaning of determinant, and once you know the matrix, then find the values of the matrix is said to be determinant, and check it out whether the determinant is invertible. Invertible mean determinant is 0, then it is singular. If it is non-singular, then it is invertible, then inverse exists. Once invertible condition used, then only we can move to the Cholesky method. And if you know the determinant value of the matrix, and we can easily find the eigenvalue and eigenvectors. If we know the eigenvalues, then only we can use the diagonalization process. After getting the eigenvectors, we can construct an orthogonal matrix, and it will be helpful to you associate with the diagonalization of the matrix. After getting eigenvalue, eigenvector, and we have to finally apply the dimensionality reduction. Once you got diagonalization, we can use the singular value decomposition SVD, and if you know diagonalization, then only we can move to the dimensionality reduction. So, it is a tree for helping the matrix decomposition. So, this is the things most important for understanding the dimension of the reduction. Now, let us go to the meaning of a determinant. So, the determinant as det of A, or sometimes is called it as modulus of A. So, that determinant of A is simply you take n cross n matrix and simply put a line, that is modulus structure like that, A11, A12 and so on. A1n, A2n, second row first column, second row third column, second row n column, n row 1 column, n row 2 column, n row n column. So, the determinant of the square matrix A in R power n cross n is a function that maps A onto a real number, and before providing a definition of the determinant for n cross n matrices, let us have a look at some motivation and examples defining determinant for some special matrices. And we have an example testing for the matrix invertible. So, let us begin with exploring the square matrix A is invertible, and we already know that when matrix is invertible, if it is 1 cross 1 matrix, then it is clearly say that capital A equal to small a equal to A inverse equal to 1 by A, thus A into 1 by A equal to 1 wholes, right, if and only if A is not equal to 0. For 2 cross 2 matrix, by the definition of the inverse matrix, A inverse equal to I. For A inverse divided, then determinant of this A11, A12, A21, A22 is nothing but A11, A22 minus A12 into A21. So, that is what they used here, and then for inverse change the places and change the sign of the opposite diagonal. Change the main diagonal and change the opposite diagonal of the matrix. So, if A is invertible, if and only if the determinant not equal to 0, that is A11, A22 minus A12 into A21 is not equal to 0. So, the quantity of determinant A in R power 2 cross 2 is determinant of A like this. A11, A12, A21, A22 is A11, A22 minus A12 into A21. This is what I written here. So, this you have to know, then we can move to the next step. For a theorem, for any square matrix A in R power n cross n, it holds that A is invertible, then determinant of A is not equal to 0. So, the closest form of the expression determinant for small matrices in terms of the elements of the matrix for n equal to 1 is det of A11 equal to A11, For n equal to 2, determinant of A is A11, A12, A21, A22, expand it, you have a 4.6. If you have a n equal to 3, then 3 cross 3, then we have a rule, that is simply A11, A11 into first A22, A23, A32, A33 minus A12 into determinant of A21, A23, A31, A33 plus A13 into determinant of what? A21, A22, A31, A32. So, this way we can expand it. So, that is the meaning of determinant. So, next we have examples of a determinant as a measures of volume. Notion of the determinant is natural when we consider it as a mapping from a set of n vectors spanning an object in R power n. So, it turns out that determinant det of A is a signed volume of an n-dimensional parallelepiped formed by the columns of the matrix A. So, the area of the parallelogram spanned by the vectors is what B and G is determinant of B comma G matrix. So, the figure 3 says that volume of the parallelepiped that is shaded the volume spanned by the vector RBG, then we can use the determinant. So, writing this vector as a column of the matrix, so A equal to RGB equal to matrix 2, 6, 1, 0, 1, 4, minus 8, 0, minus 1, and we can compute the desired volume, that is 2 into determinant of 1, 4, 0, minus 1, minus 6 into 0, 4, minus 8, minus 1, plus 1 into determinant of 0, 1, minus 8, 0. So, the net value is 186, that is the value of determinant. So, in general we have to write the determinant is called it as a Laplace expansion. So, the theorem says that consider a matrix of n cross n, J varies from 1 to n, expansion along column J, therefore, determinant of A equal to summation k equal to 1 to n of minus 1 whole power k plus j of akj of determinant of akj. So, the expansion along rho j is a determinant of A equal to summation k equal to 1 to n minus 1 whole power k plus j into A suffix jk of determinant ajk. Here A suffix kj in R power n minus 1 to n minus 1 is the submatrix of A that we obtain when deleting row k and column g. So, now let us compute the determinant of A equal to 1, 2, 3, 3, 1, 2, 0, 0, 1. So, the rule is applying the Laplace expansion. So, minor and cofactor you have to do that. So, minus 1 whole power 1 plus 1, cofactor of minor is what 1 into 1, 2, that row, that column omit it and the rest of the element 1, 2, 0, 1 and minus 1 whole power 1 plus 2 into 2 times of 3, 2, 0, 1 plus minus 1 whole power 1 plus 3 equal to 3 into 3, 1, 0, 0. So, that the net value become minus 5. So, this is the values of the determinant, and completeness we can compare the result to the computing the determinant using Sarras rule. So, this is the Sarras rule. So, this rule you have to do that and apply here, so that the same value will come. Now, for matrix of n cross n, the determinant exhibits the following properties. Number 1, the determinant of the matrix product is a product of the corresponding determinant, then determinant of AB equal to determinant of A into determinant of B, and the determinants are invariant to transposition, then determinant of A equal to determinant of A transpose. If A is a regular, then determinant of A inverse equal to 1 by determinant A, and matrix are similar, it possesses same determinant. Therefore, the linear mapping V to V, all the transformation matrix A suffix P where phi have the same determinant. Thus, the determinant is invariant to choice of the basis of the linear mapping. So, adding a multiple of column or row to another one does not change determinant A, and the multiplication of column or row with lambda in R scales determinant of A by lambda. So, in this case determinant of lambda A equal to lambda power n into determinant of A. Swapping two rows or columns change the sign of the determinant of A. Next we have a theorem. A square matrix A in R power n cross n and determinant of A not equal to 0, then the rank of A equal to n. If A is invertible, then it has a full rank. A is invertible means it is a non-singular. Non-singular means the determinant not equal to 0. Then what is the order of A? The same thing will be the rank. So, that is the meaning of theorem. Next definition. Trace of a square matrix is what is the diagonal elements of the given matrix is said to be trace of A. So, sum all the diagonal elements of the matrix, then that is called as a trace. So, they have the following properties. You take a matrix and B matrix, find the trace of A plus trace of B are equal for A and B in n cross n matrix. If trace of alpha A equal to alpha into trace of A, then alpha in R for A in R power n cross n. If trace of identity matrix is n, trace of AB equal to trace of BA for A in R power n cross k and B in k cross n. So, it can be shown that only one function satisfies the four properties together, the trace. Next we have a characteristic polynomial. For lambda in R and a square matrix A in R power n cross n, then the characteristic polynomial is a determinant of A minus lambda I is denoted by P suffix A of lambda. So, if you have a n cross n matrix, then we have a nth degree polynomial will come like this: C0 plus C1 lambda plus C2 lambda square and so on, Cn minus 1 lambda per n minus 1 plus minus 1 whole per n lambda per n. So, this is the characteristic polynomial of A. In particular, C0 equal to determinant A and C suffix n minus 1 equal to minus 1 whole per n minus 1 trace of A. Therefore, the characteristic polynomial will allow us to compute the eigenvalues and eigenvector covered in the next section. So, eigenvalues and eigenvectors. So, let A in R power n cross n be a square matrix and lambda is a scalar in R, is an eigenvalue of A, and x in R power n negation 0, then we can write Ax equal to lambda x. We call lambda is a eigenvalue, x is a eigenvector. So, the following statements are equivalent. Lambda is an eigenvalue of A in R power n cross n. There exists x in R power n negation 0, then Ax equal to lambda x. Or equivalently, A minus lambda lambda into In into x equal to 0 can be solved non-trivially, that is x is not equal to 0. Therefore, rank of A minus lambda n is less than n, then determinant of A minus lambda In is equal to 0. So, according to definition, the collinearity and co-direction, two vectors that point in the same direction are called co-directed. So, two vectors are collinear if they point in the same or the opposite direction. Note, not uniqueness of eigenvectors. If x is an eigenvector of A associated with the eigenvalue lambda, for any C belongs to R negation 0, it holds that Cx is eigenvector of A and it is same as the eigenvalue A into Cx equal to C into Ax equal to C into lambda x equal to lambda into Cx. So, all the vectors are collinear to x, then also it is eigenvector of A. Next theorem. Lambda in R is an eigenvalue of A in n cross n matrix if and only if lambda is a root of the characteristics polynomial P of lambda of suffix A of A. Next definition. Let a square matrix A have an eigenvalue lambda I. The algebraic multiplicity of lambda is a number of times the root appears in the characteristic polynomial. Next definition, eigenspace and eigenspectrum. For A in R power n cross n, the set of all eigenvectors of A associated with an eigenvalue lambda spans the subspace of R power n called eigenspace of A with respect to lambda and is denoted by E suffix lambda. So, the set of all eigenvalues of A is called eigenspectrum or just spectrum of A. Example, the case of the identity matrix. So, the identity matrix I in R power n cross n has a characteristic polynomial, then Pi of lambda equal to determinant of lambda I minus lambda equal to 1 minus lambda whole power n equal to 0, which has only one eigenvalue lambda equal to 1 that occurs n times. Moreover, Ix equal to lambda x equal to 1x holds for all vectors x in R power n negation 0. Because of this, the sole eigenspace E1 of the identity matrix spans n dimension and all n standard basis vectors R power n are eigenvectors of I. Now, we have a useful properties regarding eigenvalues and eigenvector include the following statement. Number 1, matrix A and its transpose A transpose possess the same eigenvalues, but not necessarily the same eigenvectors. The eigenspace E suffix lambda is a null space of A minus lambda I, then Ax equal to lambda x, which is equal to Ax minus lambda x equal to 0, which is equal to A minus lambda into x equal to 0. Therefore, if and only if x is a kernel of A minus lambda I. Therefore, by similar matrix possess the same eigenvalues, therefore, the linear mapping phi has eigenvalues that are independent of the choice of the basis of its transformation matrix. So, this makes the eigenvalues together with the determinant and the trace. So, the key characteristic parameter of the linear mapping as they are all invariant under basis change. When a symmetric and positive dynamic matrix always have a positive real eigenvalues. Now, we have an example computing eigenvalues, eigenvector and eigenspaces of the following matrix. Let us find the eigenvalues and eigenvector of 2 cross 2 matrix A equal to 4, 2, 1, 3. Step 1. Now, what you have to do is A minus lambda I into x equal to 0 you have to write. Here A minus lambda I contains more element than just 0. This means A minus lambda I is not invertible. Therefore, determinant of A minus lambda equal to 0. Hence, we need to compute the roots of the characteristic polynomial to find the eigenvalues. This is the step. Step 2, eigenvalues. How to find eigenvalues? The technique is P of lambda, that is determinant of A minus lambda I, that is determinant of given matrix is A 4, 2, 1, 3 minus lambda into what 1, 0, 0, 1, multiply them, we have lambda 0, 0 lambda. Then subtract these two matrix 4 minus lambda, 2, 1, 3 minus lambda. Then cross multiply these two so that 4 minus lambda into 3 minus lambda minus 2 into 1. Therefore, factorize the characteristic polynomial and obtain P of lambda equal to these two multiply. So, we have what lambda square minus 7 lambda plus 10. So, factorize we have 2 minus lambda into 5 minus lambda. Therefore, we have a two roots. One root is lambda 1 equal to 2, another root is lambda 2 equal to 5. So, next we have to find out the eigenvectors and eigenspaces. So, we find the eigenvectors that corresponding to eigenvalues, we have to do A minus A into x equal to 0. So, what you have to do A minus lambda I into x equal to 0. So, A minus lambda into x is 4 minus lambda 2 1 3 minus lambda into x1 x2 equal to 0. So, 0 can be written as this. Now, what you have to do, you have to put lambda equal to 5, two values got it, first you take lambda equal to 5. So, 4 minus 5, 2, 1, 3 minus 5 into x1, x2. 4 minus 5 is minus 1, 2, 1, minus 2 into x1, x2 equal to 0. Therefore, we solve the homogeneous system to obtain the solution space E5 equal to what, this minus x1 plus 2x2 equal to 0. Another you say x1 minus 2x2 equal to 0. So, this implies x1 equal to 2x2. So, if you choose what x2 equal to 1, then x1 equal to 2. So, that is what they written here. So, the eigenspace is a one dimensional as it possesses a single basis vector. So, the analogy we find the eigenvector lambda equal to 2 by solving the homogeneous system of equation. We have another equation is 4 minus 2 2 1 3 minus 2 into x, which is equal to 2x1 plus 2x3, that is you have x2 x3 you have to take it, this is x3 x4 you take it, therefore x3 x4 equal to 0 means what, x3 plus x4 equal to 0, therefore x3 equal to minus x4. Therefore, if you choose x4 as 1 and then x5 equal to minus 1 or vice versa. So, we have this. So, this is the meaning of what eigenvector, therefore, E2 span 1 minus 1. Next definition is geometric multiplicity. So, lambda I be an eigenvalues of the square matrix A, then geometric multiplicity of a lambda is a number of linear independent eigenvector associated with lambda I. In other words, it is the dimensionality of the eigenspace spanned by the eigenvector associated with lambda I. So, note is specific eigenvalues geometric multiplicity must be at least 1 because every eigenvalue has at least one associated eigenvector. So, an eigenvalue's geometric multiplicity cannot exceed its algebraic multiplicity, but it may be lower. So, you take a matrix A 2 1 0 2 has a 2 repeated eigenvalues, lambda 1 equal to lambda 2 equal to 2 and then algebraicity is 2. So, if you have eigenvalue has only one distinct eigenvector, then geometric multiplicity is 1. So, this is the way we can find out algebraic multiplicity and geometric multiplicity. Next, graphical intuition in 2 dimensions. Let us gain some intuition for deterministic of the determinants. So, let us gain some intuition for determinants, eigenvectors and eigenvalues using different linear mappings. So, figure 4.4 depicts 5 transformation matrices A1 to A5 and their impact on the square grid of the points centered at the origin. So, A1 equal to of 0 0 2, the direction of 2 eigenvector corresponding to the canonical basis vectors in R square to 2 cardinal axes. So, the vertical axis is extended by the factor 2, the eigenvalue lambda 1 equal to 2 and the horizontal axis is compared by the factor of eigenvalue lambda 2 equal to of the mapping area of preserving determinant of A1 equal to 1, which is equal to 2 into 1 by 2. So, A2 equal to 1 of 0 1 corresponding to sharing A2 equal to 1 of 0 1 corresponding to shearing mapping, that is it shears the points along the horizontal axis to the right if they are on the positive. So, this is the corresponding picture representation of choosing the lambda 1 lambda 2. So, the first figure says that lambda 1 equal to 2 and lambda 2 equal to 0.5 and then find the determinant of 1, the corresponding mapping like this. And then if lambda equal to 1 and lambda 2 equal to 1, the determinant A is also 1, then the corresponding mapping represent like this. And similarly, lambda equal to 0.87 minus 0.5 j and lambda 2 equal to 0.87 plus 0.5 j. If you have a determinant 1, then the mapping is in the form of the complex and reflect like that. If lambda 1 equal to 0 and lambda 2 equal to 2 and determinant equal to 0, it becomes the what straight line and what based on minus x axis to what reflect on the, this is y and this is x and minus x and this is y and minus y. So, it reflect like that. So, this is the determinant of eigenspaces overview of the linear mapping and their associated transformation matrix. So, it is a 400 color coded pointed on to target point AIX. The central column depicts the first eigenvector stretched by its associated eigenvalue lambda 1 and the second eigenvector stretched by its eigenvalue lambda 2. Each row depicts the effect of one of the 5 transformation matrices AI with respect to the standard basis. So, half of the vertical axis and the left vice versa matrix also determine. So, this mapping is the area of preserving determinant of A2 equal to 1. So, the eigenvalue lambda 1 equal to 1 equal to lambda 2 is repeated, then eigenvector are collinear. This indicates that the mapping acts only along one direction. Next, A3. Suppose we have a cos of pi by 6 and minus sin pi by 6, sin pi by 6, cos pi by 6, the value is this. So, the matrix A3 rotates points by pi by 6, that is radian is 30 degree counterclockwise and has only complex eigenvector that reflect the mapping is a rotation. A rotation has to be volume preserving, so the determinant is 1. The more details of the rotation and refer the section. Suppose A equal to 1 minus 1 minus 1 1 represent a mapping in the standard basis, then it collapses the 2-dimensional domain onto a 1 dimension. Since one eigenvalue is 0, the space direction is a blue eigenvector corresponding lambda 1 0 is collapses, while the orthogonal red eigenvector stretches space by the vector lambda 2 equal to 2, therefore, the area of image is 0. A5 equal to 1 and 1 by 2 is a shear and stretch mapping the scale space by 75% since determinant of A5 equal to 3 by 4, it stretches space along the red eigenvector lambda 2 by the vector 1.5 and compresses it along the orthogonal blue eigenvector by a factor 0.5. So, this is the eigenspectrum of biological neural networks, and method to analyze and learn from network data are the essential component of a machine learning methods. So, the key to understand networks is a connectivity between network nodes, especially if two nodes are connected to each other or not. In data science application, it is often useful to study the matrix that capture this connectivity data. So, this is the eigenspectrum corresponding to the connectivity matrices. Next, we have a theorem. So, the eigenvector x1 to xn of the matrix in n cross n with n distinct eigenvalue lambda to lambda n are linearly independent. So, the square matrix A in n cross n matrix is defective, it possesses fewer than the n linearly independent eigenvectors. Next, we have a theorem. Given the matrix A in R power m cross n, we can always obtain a symmetric positive semi-definite matrix and S in R power n cross n by defining S equal to A transpose A. So, the rank of A equal to n, then S equal to A transpose A is symmetric and positive definite. Next is spectral theorem. If A belongs to n cross n symmetric, there exists an orthogonal basis of the corresponding vector space V consisting of eigenvectors of A and each eigenvalue is real. So, the direct implication of the spectral theorem is that the eigen decomposition of the symmetric matrix A exists, that we can find a ONB of orthogonal normal basis of the eigenvector, so that A equal to PDP transpose, where D is a diagonal and column of P contain the eigenvectors. Now, consider matrix A equal to 3 cross 3 matrix 3 2 2 2 3 2 2 2 3. The characteristic polynomial of A is polynomial of lambda equal to minus lambda minus 1 the whole square into lambda minus 7. So, we obtain two eigenvalues, one is lambda 1 equal to 1 and lambda 2 equal to 7. So, the technique of finding the eigenvector is A minus lambda I into x equal to 0. So, we have three eigenvalues, lambda 1 equal to 1, lambda 2 equal to 7 and lambda 1 equal to 1 is repeated. Once it is repeated, we have a minus 1 1 0 or minus 1 0 1 because these two should be orthogonal. And another eigenvalues, that is E2 equal to span of 1 1 1 for x3. We see that x3 is orthogonal to both x1 x2. So, x1 transpose and x2 multiply them, we have a 1 which is not equal to 0. So, x1 is minus 1 1 0 and this one is minus 1 0 1. So, multiply them, minus 1 into minus 1 is 1 plus 0 which is equal to 1, that is what they return. So, they are not orthogonal, then it is become 0. State that there exists orthogonal basis, but the one way we have is not orthogonal, we can construct one. So, to construct such a basis, we exploit the fact that x1, x2 are eigenvector associated with the same eigenvalues lambda. Therefore, for any alpha comma beta in R, then A into alpha x1 plus B into x2 equal to A x1 alpha plus A x2 beta, which is equal to lambda into alpha x1 plus beta into x2. So, in any linear combination of x1 x2 is also an eigenvector of A associated with lambda. So, according to Gram-Smith algorithm is a method for iterative constructing of an orthogonal and orthonormal basis from a set of basis vector using such a linear combination. Therefore, even if x1 and x2 are not orthogonal, we can apply the Gram-Smith algorithm and find the eigenvector associated with lambda 1 equal to 1. So, that are orthogonal to each other. Therefore, our problem we will obtain x1 dash equal to minus 1 1 0, x2 dash equal to 1 by 2 into minus 1 minus 1 2. So, which are orthogonal to each other, therefore, orthogonal to x3 and eigenvectors of A associated with lambda 1 equal to 1. So, the determinant of matrix A in n cross n matrix, the product of its eigenvalue is determinant of A equal to product of I equal to 1 to n lambda I, where lambda I are a possibly repeated eigenvalues of A. Now, we have a geometric interpretation of eigenvalues, the eigenvector A get stretched by the corresponding eigenvalues, the area of the unit square changes, the modulus of lambda 1 lambda 2, the perimeter change by the vector of half into modulus of lambda 1 plus lambda 2, modulus of lambda 2. So, the trace of matrix A in n cross n matrix is sum of the eigenvalues, which is trace of A equal to summation I equal to 1 to n lambda I, where lambda I in C is eigenvalues of A.